Welcome, fellow chemists. Today's video is the first of three in a series on writing chemical formulas, and we will focus specifically on binary ionic compounds with monatomic ions. Atoms, as you know, have equal numbers of protons and electrons, meaning they have zero charge or are neutral. One ion has more protons, resulting in a positive charge, and is called a cation. The other ion has more electrons, which means it is negatively charged, and is called an anion. How can we remember those names? Well, here's a suggestion. The T in the word cation is kind of like a plus sign in the middle, and anion literally spells it out, a negative ion. Knowing we have a cation or anion is great, but even more helpful is knowing the magnitude of the charge. Sodium atoms by definition contain 11 protons along with 11 electrons. There's no charge, so the symbol could be written like this, but convention drops to zero. Should sodium lose an electron, it now has more protons. The symbol reflects this change as the difference in the charge or magnitude is 1, and is positive since there are more protons. If a sodium atom gains an electron, it would have more electrons. The symbol for this ion has the same magnitude as before, but since there are more electrons, it is negative. Though ones are not typically shown, this is the conventional way of writing ions with the magnitude before the sign. However, I'm going to switch them around like this. I prefer writing it this way when teaching for a reason which will be evident shortly. Since we are only referencing the ions to develop the formula, it really does not matter how we write them. Let's consider the compound composed of sodium and fluoride ions. When we have one cation and one anion, they form a binary ionic compound. In this video, all ions are monatomic as they are composed of one atom. To make the correct formula, the charges must cancel, and we use subscripts to indicate how many ions are needed. With a +1 and -1 ion, it's pretty easy to see that bringing together one of each ion cancels out the charge. Since the charges cancel, they don't appear in the final formula. Subscripts show how many of each ion are needed, but it is unnecessary to include a subscript 1. When the ions have equal but opposite charges, the formula is quite easy to figure out. With magnesium and oxide, the charge may be twice as big, but they cancel out all the same, giving us the formula MgO. Even with aluminum and nitride, where the charges are even bigger, one of each ion results in a full cancellation of charges. And it does not matter what the charges of the ions are if they cancel out. To make the formula, just remove the charges and put the symbols together. However, what about when the charges don't cancel out? In the case of potassium and sulfide, the charge with one ion each is -1. Add another potassium and the charge becomes 0. This results in the formula K2S. Similarly, with chromium and chloride, the charge is +2. Add another chloride and it's +1, and a third chloride makes it 0. This gives the formula CrCl3. With calcium and phosphide, the total charge is -1. Add another calcium and it's +1. Another phosphide, it's -2, which means a third calcium is needed to get it to 0, making the formula Ca3P2. So, did you see it? Okay, do you see it now? I've put the ions and formulas back. In all these examples, the magnitude of the charge ends up in the formula. This means we don't need any fancy accounting. Simply turn those charge values into subscripts. In fact, Criss-Cross will make you jump for joy now that you have an easier way of making formulas. But there is a slight problem with it. Crisscross the charges here and you get Pb2O4. However, if you chose the longer accounting way, then simply adding another oxide would have sufficed. That formula is PbO2, so which one is correct? Formulas for ionic compounds indicate the simplest ratio possible, so PbO2 is preferred over Pb2O4, and we can get there by simplifying the subscripts. This allows us to continue using the crisscross method successfully. Now for the formalities of this and that. Binary ionic compounds are composed of a cation and an anion. In the accounting method, add ions until the overall charge cancels. The number of ions needed are then written as subscripts except for one. Crisscrossing guarantees the charge balancing. After switching subscripts, ensure they are simplified if necessary. Practice problems are on the horizon with all ions from the lists linked in the description. If you have any questions or requests, leave them in the comments. Best of luck, and as always, thank you very much for watching.